So this is the first lecture in 2 of substitution with definite intervals. And what I'm going to do is to move very slowly at first and draw some pictures so that you can understand what is happening. And then we'll come back and do a couple of examples where we move more quickly so that you can see how we actually do this in a while. Today I'm going to talk substitution. Tomorrow I will talk about repair, which in some senses is easier, or substitution done mentally. I want to consider a relatively straightforward looking integral, the integral from 0 to 3 of root x plus 1 dx. What we'd like to do is to be able to use the fundamental theorem to find this integral. And we observe that to do that I need an antiderivative, and if I need an antiderivative, I'm going to need to substitute u equals x plus 1. So, I go ahead and set up my substitution here, u equals x plus 1, and I find the du, which you guys all know how to do. But before I do, I look and I see that I have these limits of integration right here, and I wonder what's going to happen to them when I substitute. So to get at that question, I'd like to draw a picture to get a clear idea of what I'm doing. The integral right here represents the net signed area under the curve of the region bounded by y equals root x plus 1, from x equals 0 to x equals 3. And this integral is equal to that area, the value of that area right there. When I pull off the substitution u equals x plus 1 and du is equal to dx, I'm going to end up with a new region that you can see actually looks just like the old region, except that it has been shifted to the right by 1 meter. So that instead of root x plus 1, the graph of my region now looks like the net signed area underneath the curve y equals root u. And what I've done is really to take this entire region and just shift it over by 1. When I do, not only do I shift the curve over, but I also shift the limits of integration over. So that my limits of integration are no longer 0, 3, but now they are 1, 4. And here I argue geometrically that these limits of integration would be transformed from 0 to 3 into the interval 1 to 4. But I could also have done it algebraically, because I can observe that when x is equal to 0, since u is x plus 1, therefore u is equal to 1. And when x is equal to 3, then since u is x plus 1, then u is equal to 4. So that the limits that correspond to x equals 3 and x equals 0, the corresponding u values are u is equal to 4 and u is equal to 1. Just like that. In other words, when I go substituting, I have to substitute everything in terms of u, including the limits of integration. They have to be u values and not x values. Now, let's go ahead and carry out this integration and get a value, and then I want to come back and make a point about that value. Go ahead. Go ahead and integrate. The integral from 1 to 4 of root u du is. what antiderivative rule you're using.
No, it's due to the 1 over 2.
Sure. Yep.
Minus 1.
Why? Why
Oh,
minus
plus
1?
1.
Ah.
Plus all over 2. Which is 2 over 3
Uh-huh.
times u to the 3 over 2.
Yeah. Now, because we've got derivatives and integrals all jumbled up in our head, check that. Take a derivative, see if it checks out. Yeah, okay, good. Got our head straight again. And we're going to evaluate that from 1 to 4. And so that gives us 4 to the 3 halves minus 1 to the 3 halves. What is 4 to the 3 halves power? 8. That's right. The square root of 4 is 2. Raised to the 3rd power is 8. Minus, of course, 1. And that gives me 14 over 3 as my area. Yes, sir?
Oh, you do the derivative, don't need plus c.
Ah, great question. Do I need the plus c? Let's say that I had a plus c in here. Any constant that I have whatsoever, the c will cancel when I subtract. So I might as well pick the easy c, which is 0. Great question. So the plus c is not wrong, but it also doesn't make a difference. Okay, now here's the point that I want to make. When I come back to this region now, the answer that I got for the area was 14/3. That's the area of this region right here. That's 4, so let me try that again. 14 is the area of my region. This area right here is exactly the same area as the area of this region. How do I know? Because I went through and I replaced quantities with what they were equal to. If u is x plus 1, then everything else in here is equivalent. Which means that I ended up with 2 different looking integrals with the same value. So the spirit of substitution is that you're taking one region and you're pulling off a substitution to transform it into a different region that has the same area, the same net size area. Yes?
So you don't have to convert u back to x or anything?
Exactly. No back substitution is required because I replaced my original interval with one that is equal to it. I find its value and I'm done. And we like that. There's no back substitution needed. So that is different from the antiderivatives that we do.
How do we always find the right number?
What's that?
How do we always find the right number? Because for this one, we change 0 to 3
Oh,
to 1.
yep. And we did that. It wasn't arbitrary. We did that on the basis of taking these two x values and plugging them into u.
For some equations that it's not easy to find.
Right. So finding the right u is an art form. And I've given you a couple of really good strategies to try, right? Inside functions and entire denominator. And then for certain circumstances, through experience, you might say, all right, I know this u will work well because we'll actually see one later today. It's like, okay? So, a lot of things to learn here, but the moral of the story is found in this boxed thing right here, which is that when you replace in terms of u, don't forget to substitute out the limits of integration. The biggest mistake that I see students make is to successfully convert the integral in terms of u, and then they get lazy and they just copy these numbers down. Wrong. These are x values. These are the corresponding u values you have to replace. If you don't, you end up with a different region with a different area. Okay? Okay. Let's look at another one that's slightly more complicated. In the previous example, this was kind of easy because my region just shifted to the right. Now we're going to see one where the region transforms and looks really different. Let's consider the integral from 0 to 1 of x over 1 plus x squared dx. Now again, we're going to take our time with this one so that we can see what's going on. And if we sketch the function y equals x over 1 plus x squared, it looks something like this. And the region that we're talking about is the region from 0 to 1. Okay. Now we observe, and it seems like substitution might be a good idea. Any suggestions for a u? Absolutely. Let's look. U equal 1 plus x squared. And du? Dx. Good, good, good. And now, for the limits of integration, I'm going to compute u of 0, and I'm going to compute u of 1. And what is u of 0 equal to? And u of 1? Yep. So that my integral now transforms to the integral from 1 to 2 of x dx is the same as 1/2 of du, and 1 plus x squared is u. Now if I look at the region that I have transformed into, I have a really different looking region. The graph of y equals 1/2 over u or 1 over 2u looks like this. It's got a vertical asymptote, so it looks nothing like that region right there. However, when I integrate that region from 1 to 2, what I'm going to get is an area that is the same value as the shaded blue area right here. These two don't look the same, but they have the same area. How do I know? Because I replaced everything in terms of x into the corresponding u values.
So we can take the constant numbers along.
I will. I just was illustrating what's going on right here. Yep. Now that I've done this, I'm going to focus I'm going to draw a mental line. That integral's done. I have substituted away everything, and I'm going to evaluate this integral right here, and the value of this integral is the value of the original. So out comes the 1/2, as Tony suggested, and I get a famous integral du over u. What is it? Yep. From u equals 1 to u equals 2. So I get 1/2 of ln2 minus ln1. Don't forget to put parentheses around your evaluation right there. Do we know any of these numbers? ln2 is ln is 0. Yep. So we get 1/2 of ln2. I thought you were going to tell me this. 6 and 1.
I'm trying to do this like gallon too, so
How are we doing? Now, in the wild, I don't usually draw these pictures because I have confidence that the substitution process works. So the main things that we're going to focus on when we actually do these are found right here. Find your u, find your du, compute the new limits of integration, substitute, and evaluate. Does that make sense to everybody? Okay, cool. How about? What do you think? Good. Let u equal 1 plus sine x. Keep going.
So the whole thing just gone. We have used
Well, I think we need to find
U zero and U.
Yeah, it's good. So what is u of 0 equal to? And also 1. Ooh, he hesitated. Because it makes our integral interesting, doesn't it? By the way, what am I missing right here? D, right? Yes! Whoa, really? Uh-oh, we better draw a picture. Yep. Sure enough it is. When I graph y equals 1 plus sine of x squared times cosine x, I get something really interesting. I get a region that looks something like this. And all of the plus area right here, and all of the minus area right here are the same but opposite, and they cancel out to give me 0. So this was kind of cool, and it happens. Notice that although these two have the same area, they do not have the same shape in the least. This has a net signed area that looks like this, and the region here is a region of 0 width. So that can totally happen. Let's see. I want to consider now this integral.
inverse.
Which one? She can't remember. Guys, this, what's that? 5 over x? I'm going to put a big question mark here because we can't remember the antiderivative. This is the limitation of relying on brute memory. The formulas can get complicated and we're not sure which is which. And so instead of relying on brute memory, very often I rely upon remembering how it works. And you may remember that for all of our inverse trig forms, we pulled off a substitution, and it was the same substitution every time, and it relied on the fact that I wanted to get a common factor of 25 when I substitute. And if I want to get a common factor of 25, then my indicated substitution will be x equals 5u. So that when I square 5u, I will get 25u squared. So let me pull off that substitution so that we don't have to rely on our faulty memory string. It's actually x over 5. Yep. So I let x equal 5u, dx equals 5 du, and now we can go through plugging in everything. We get dx is 5 du, x squared will be 5u quantity squared. But what about those limits of integration? These limits of integration are x values. So when I come back and substitute them in for x, I find that when x is 5, u is equal to 1. And when x is 0, u is equal to 0. So that my integral now transforms into this integral right here. This needs a little bit of cleanup, but it's not nearly as fearsome as it looks. 5 comes to the outside there, and 5u squared, quantity squared is 25u squared plus 25, and right here is the payoff for my substitution, that common factor of 25. So out it comes. inverse tangent of u. That's exactly right. So I get 1/5 of arctan 1 minus arctan of 0. Don't forget your parentheses. What is the inverse tangent of 1? Yes. And inverse tangent of 0? Just 0. So that my result is pi over 20. So the moral of the story is that remembering how to get our results is sometimes a little bit better than the brute memory. But here's the thing. Eventually I get tired of substituting like that, right? And so I work it out for myself, and I realize, okay, what I got was 1/5 of inverse tangent of u, and u is x over 5, and so I get the form right there. So eventually you will remember it, but only because you've gotten tired of deriving it. Does that make sense? Okay, let's do more examples. Like this. Actually, that'll work. This I would put in a more complicated example category. Talk me through it. That seems like a good start. Good, good. Let's put together the pieces that we can so far. Good. Skip that. Not sure about that just yet. This part, the square root of u. Now, let's come back to this. Here's where I need, do you guys remember how I jumped up and down and fussed and said no mixed forms? Remember that? Can't put x's and u's together in the same interval? Here's why. I have u values now, no longer x values. If I put an x value in there, and if I put x in right there, I now have two different variables going on. Bless you. To which variable do these limits of integration correspond? See the problem? So we can only have ever one variable at a time. That means I need to replace x, and that means I need to know what x is. Do we have any clues as to what x is? Aha! That's exactly right. A little bit of algebra gives it to me. X is u minus 1 over 2. And so I can now substitute here. Like that. Now it's ugly, but before I panic, I'm going to do the necessary algebra and see if anything nice pops out. Out comes a factor of 1/2 here, and out comes a factor of 1/2 here, so that I get 1/4 on the outside. Don't forget parentheses because the horizontal bar is a grouping symbol. And I'm going to rewrite the square root of u as u to the 1/2. Aha! This is getting clearer. Because this, I can now distribute and get the integral of u to the 3/2 minus the integral of u to the 1/2 du. And this gives me like so. And this is sort of a pain in the neck, but I can do it. U to 9 to the 5/2. Square root of 9. 3 to the 5th power. Not sure. Let's write that as 3 to the 5th. What's that? Yeah, 243. Yep. Yeah, because it's 81 times 3. Yep, 243. Minus 2/3 of 3 to the 3rd, which is 27. Don't forget that you're grouping here. 2/5 times 1 to the 5/2 is 1, and 1 to the 3/2 is 1 also. Can I simplify this? Yes. Should I? Probably not. That's a number. We're done. So this was a more complicated example really for a couple of reasons. One is that I ended up with a spare x left over that needed to be substituted. And the second reason that it was a little bit more complicated is that once I had substituted, I ended up with an integral that required a little bit of algebra to handle. And the third reason is that once I had actually integrated it, I ended up with a fairly complicated numerical result that I don't really feel compelled to simplify. How are we doing? Okay. Let's consider one more issue. Go. And if you're watching along at home, I will pause the recording. You do this one too. Okay, and welcome back. So here, we observe that u equals the inside function is a good choice. We go ahead and compute the du, negative 2x dx, like so. And we also compute the new limits of integration. U of 0 is 0, and u of 1 is negative 1. Now, the reason I wanted to point this out is that when we come back to do our substitution now, the limits of integration look wrong because 0 corresponds to 0, 1 corresponds to negative 1, and all of a sudden I'm integrating backwards. That's okay. Please resist the temptation to just rearrange these without using the reversal property, just because one is larger than the other. They have to correspond. 1 is going to correspond to whatever it corresponds to. And 0 is going to correspond to whatever it corresponds to. And if I need to fix that later with some properties, I will. But this is where it is. So, then e to the negative x squared is going to be e to the u. X dx is the same as negative 1/2 of du. Like so. And now I can pull the negative 1/2 to the outside. And I can also use my reversal property to clean up my integral just a little bit. Flip the limits of integration and take the opposite to get a really nice result. E to the u, negative 1 to 0, which is 1/2 of e to the 0 minus e to the negative 1. What's another way to spell, what's another way to spell e to the 0? Yep, and what's another way to spell e to the negative 1? 1/8. Well, now again, if we consider what we did here, the original integrand refers to a function that looks something like this, like so, and I'm integrating from 0 to 1, so I should get a positive value right there, and that value is 1/2 minus 1/2e. Not in 4 places. 0. Okay. But when I pulled off the substitution, I had a completely different region, e to the u, just like this, and I'm going from, it's actually 1/2 of e to the u, and I'm going from -1 to 0, completely different region, but with the same area. Does that make sense? Okay. Tomorrow, we'll talk about how this looks like with repair. Your homework problems for tonight are reassigned tomorrow. Tonight, you're going to use substitution on them. Tomorrow, you're going to use repair. Okay?